another video on KBC. So in this video we'll see the circuits to find the MOSFET drain current. These are the prerequisites you should know. Okay, with this introductory thing, let us move on to finding the drain current of this particular circuit. So now there are two voltage sources V1 V2 are given. So this V1 is connected to gate through a resistor RG. We know that gate current of a MOSFET is 0 in magnitude because this is isolated. So since there is no current, so the drop here is 0. So whatever is V1 will be applied between the gate and the source. So now I can write VGS is equal to V1 is equal to 0.7 volts. Since threshold voltage is 400 millivolt and applied gate to source voltage is 700 millivolt, we have a condition VGS is greater than VTH. So MOSFET is in on condition. So once it is on, so I know that it should be in either linear or saturation. So for it to be in saturation, we know that VDS should be greater than VDS saturation. So for this VGS, so we can find what is VDS sat, which is nothing but VGS minus VTH, which will be 0.7 minus 0.4, which is 0.3 volt. And VDS for this circuit, as you can see here, this V2 happens to be VDS, which is equal to 0.7 volt. So from this and this, so this is actually VDS sat. So from this we know that VDS is greater than VDS sat, that is 0.3 volt is greater than 0.7 volt. In such case, I can use the expression of ID in saturation region, and I can write the expression of ID is equal to half Kp W by L VGS minus VTH whole square. So by substituting all the values, I know Kp as 200 micro and W by L is given as 60, and this is 0.7 minus 0.4 whole square. This comes out to be, it's 60 into 0.3 square, it comes out to be 5.4 into 10 power minus 4 ampere. On pressing engineering, it is 540 microampere. So this is the drain current is 540 microampere, correct? This is as simple as it is. So let us move on to the next question. So now there is a resistor over here. So there was a resistor of 100k in this gate side. This was not making any significance because there was no current flowing through this. Now we have a resistor in connected to drain, that is 10 kilo ohm. So now since current flows, so there will be some drop here. So now if I say this as V1, this as V2, now naturally we know that V1 is coming across the gate and the source, so that V1 happens to be VGS, which is now 0.5 volt, which is greater than certainly V threshold. So MOSFET is on. The MOSFET is on. Once it is on, we know that it can be in either linear region or saturation region. So out of these two, in which region it is there, that depends on what is the value of VDS. Whether VDS is less than VDS sat or VDS is greater than VDS sat. So this will say less than or equal to. Even if it is equal to VDS sat, we say it as it's in verge of saturation region or verge of linear region. It's exactly this point. So this is what we are talking about. This is the verge. This is ID, this is VDS sat, this is VDS. So here beyond this it is saturation, before this it is linear. So at this point we say it is verge. Now assuming ID in saturation region, let me estimate what is the drain current. It is half Kp W by L VGS minus VTH whole square. So that current comes out to be, so now here it is half into 200 micro into 60 into, it is now 0 0.5 minus 0 0.4 whole square. So if I substitute, it is 100 exponential minus 6 into 60 into 0.1 square, which happens to be 60 microampere, correct? So this is, so it is now 60 microampere is ID. So now if this much amount of current flows, let us find what is VDS. So from KVL, sorry, from Kirchhoff voltage law, we can write VDS is equal to V2 minus ID into RD. So how much is V2? This is given as 0.9, and we have this as ID is 16 micro, and this is 10 kilo. So now this comes out to be 0 0.9 minus of 60 exponential minus 6 into 10 exponential of 3. So it is coming out to be 0 0.3 volt. So this is VDS. Since VDS is 0 0.3, how much is VDS at here? So for this VGS, for the VGS of for the VGS of 0.5 volt, VDS at is VGS minus VTH, which is nothing but 0.5 minus 0.4 is equal to 0.1 volt. This is VDS sat, but VDS is 0.3. Therefore, VDS is greater than VDS sat. So MOSFET is in saturation region. And the ID is equal to 60 microampere. Correct? So this is ID. Let me just again find it. It is 100 exponential minus 6 into 60 is WL into 0.1 whole square. So it is 60 microns. So this is correct. So this is also in saturation region. Saturation region. Because VDS, this is plus minus VDS, is less than VDS. Let me proceed to next. Let me find what is ID of this. Shall I take it as 100 kilo ohm for some clarity? Okay, for some difference. So let me again consider V1 is now equal to VGS, which is 0.6 volts, and I can assume this in saturation region and find the ID. So which is nothing but half into Kp W by L VGS minus VTO or VTH whole square. This comes out to be, so it is now half into 200 micro into 60 into 0.2 whole square. It is now 100 expression minus 6 into 60 into 0.2 whole square. It comes out to be 240 microampere is AD in saturation. So therefore, with this VGS, how much is VDS at? VDS at is nothing but VGS minus VTH, which happens to be 0.6 minus 0.4, which is 0.2 volt. So this is VDS at. So let me find what is VDS, which is nothing but VDD minus AD into RD. So this comes out to be 1.8 minus 240 microampere into 100 kilo. So this comes out to be, so now what you have, it is 1.8 minus of 240 exponential of minus 6 into 100 exponential of 3. So this comes out to be minus 22.2 volt. Oh, we have this VDS value negative, which is not a possible case. So when you have a supply voltage of positive 1.8, you cannot have VDS as minus 22.2 volts. So our assumption, so we assume that our assumption of MOSFET M1 in saturation is wrong. This is wrong. So I have to consider the linear equation. So what is ID linear? It is half into Kp W by L to VGS minus VTO into VDS minus VDS square. This is VDS square. So what is VDS? VDS is equal to VDD minus ID RD. Wherever VDS is there, replace it by this. So then this comes out to be ID linear is equal to half Kp W by L. It is now 2 VGS minus VTO into VDD minus ID RD minus VDD minus ID RD whole square. Let me solve for ID. So I know everything except this. So except this ID, I know everything. So this I know, 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 everything I know. So let me find out. So it is alpha A, alpha equals 100 exponential of minus 6. Okay, let me just redo it. Sorry. This is alpha A, alpha equals 100 exponential of minus 6 into 60 into open the parenthesis 2 into open the parenthesis. This is 0 0.6 minus 0.4 into open the parenthesis 1.8 minus alpha A into RD is 100 exponential of 3 close minus of open the parenthesis 1.8 minus alpha A into 100 exponential of 3 close square root close shift cal. So I'm getting the value of ID as, let me find out the ID of the value of ID is coming out to be, it is 17.92 microampere is one of the value. Let me find the other value. The other value is okay, it is coming out to be the same. So let me find the other value as equal to minus of 1. So I'm finding both the values. Okay, other value happens to be 14.05 microampere. So I have two values of ID because it's you have a square there. So let me find which value is correct. By considering this value of ID as 17.92, let me find VDS. Considering this as 14.05, let me find VDS. So VDS with ID as 17.92 microampere is, that's what is 1.8 minus of alpha A into 100 exponential of 3. Calculate for this value is coming out to be, this is for 14.05 microampere. The VDS is coming out to be, 0.394 volt. Let me calculate for 17.92 exponential of minus 6. If I find out, that comes out to be 8 millivolts. 8 millivolt. So now you have VDS with this as the current. This as the current is coming out to be 8 millivolt. With this as the current, it is coming out to be 0.394 volt. That is 394 millivolt. How much is VDS at? VDS at is actually 200 millivolt. So this is VDS SAT. I have two values of VDS now. One of the VDS is 8 millivolt. Other VDS is 394 millivolt. You may can see we have assumed the MOSFET to be in linear region. Of course, when we started with it to be in saturation region, we got a current of 240 microampere, which is hardly not possible because you are coming out, you are getting VDS as minus 22.2. So now you consider this to be in linear region. When you consider MOSFET is in linear region, then VDS has to be less than VDS sat, correct? So now, out of these two, which is less than 200 millivolt. So this is less than 200 millivolt. Which is the current corresponding to this 8 millivolt VDS? It is this current. It is this current. So with a current of ID is equal to 17.92 microampere, I'm getting a VDS of 8 millivolt. So naturally, the current flowing through this is 17.92 microampere. This is the current that is flowing. Hope you got it. Let me again repeat. We started everything as usual. We assume that MOSFET is in saturation region. We found what is the saturation current, because there is no harm in starting with that as assumption as saturation region, because that is the easier equation. So you found out that because in the previous two cases it was assumed as saturation region and it was in saturation region. So here we assumed it as saturation, but it is coming out to be negative VDS, so which is not a possible, practically possible case. So naturally you have to assume the MOSFET in linear region. When you assumed it as linear region, this is the equation. So in this equation I have a VDS. So this VDS need to be substituted by this, because I don't know what is VDS is. So VDS by equation is VDD minus ID into RD. That's what I substituted. Then I'm solving for this. So that's where the calculator is so handy. Otherwise, this is a mathematical problem. So I have to solve this using calculator. I'm getting two currents because there's a part of your quadratic equation. When you have two currents, naturally you need to choose one of them. So only one is electrically correct. So now when I took this current and found out VDS, I got it as 8 millivolt. When I took this as my ID, found out VDS, because I know how to find VDS. So VDS is coming out to be this current. So sorry, these voltages. So I have 8 millivolt and 394 millivolt. Out of these two, this is not a voltage which keeps the MOSFET in linear region, because here we consider it as linear region. So naturally this is not in linear. So VDS of 8 millivolt is a possible linear region operation. So corresponding ID is 17.92 microampere. So current flowing through this circuit is the drain current is 17.92 microampere. Fine. So let us move on to this. Now you have this potential divider R1, R2 along with VDD will decide what is VGS is. So now VGS is given by VDD into R2 by R1 plus R2. So once you know that, I can assume it is in saturation region. Write the equation of Kp W by L VGS minus VTO whole square. VTO or VTH. Let me find out this. And let us later verify what is VDS. VDS is equal to VDD minus ID RD. Let us also find what is VDS sat here. And let us compare VDS. Is it greater than VDS sat or not? If it is greater than, then our assumption is correct. So this is 1.8 into 150 divided by 350. So it is 0.771 volt. So this comes out to be 0.371 volt. So then this is 100 exponential minus 6 into 60 into 0.371 whole square. The current is 825.8 microampere. With this much ID into 800 minus of 1.8. Okay, this is coming out to be 1.13 volt. So of course I just made this reverse. Okay, this is 1.13 volt. So 1.13 is certainly greater than 0.371. So our assumption of ID, sorry, MOSFET in saturation is current. The ID here is 825.8 microamperes. Correct? Since we assumed it is in saturation region, we found the current, then found VDS, then compared VDS with VDS sat. So this is perfect. So our assumption of MOSFET in saturation region is perfect. Okay, now let us see this. So now there is a resistor source. Now this is VGS. VGS is nothing but VG minus VS. So what is VG? 0.9. What is VS? The same ID flows here. The same ID flows here. It is ID into RS. So this is VGS. Of course, RS we know it as 100 ohm. So let me find the expression for ID. ID is equal to half Kp W by L VGS minus VTO whole square. Now you replace VGS by this. So ID is equal to half Kp W by L. It is 0.9 minus ID into 100 minus 0.4 whole square. So I know everything except I know this, 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 except this ID. I know everything. So let me solve for ID, two values of ID. So this is ID 1 value and ID 2 value. So let me find this. Alpha A, alpha equals 100. Let me do it. Alpha A, sorry, alpha equals 100 exponential minus 6 into 60 into 0.9 minus alpha A into 100 minus 0.4 whole square, shift cal. So one of the value of ID is 973 microampere. The other value is equal to, make it as maybe 1 exponential minus 6 equals shift cal. So this is the least value. Let me find the other value equals 1 equals shift cal. So other current is 25 point, okay, plus engineering, it is 25.6 milliamperes. So out of these two currents, which current is correct? So this cannot be 25.6. So actually this has to be this. Suppose you assume the current as 25.6 milliamperes, then okay, let me find what is VDS is. So VDS, I know that it is VDD minus of ID into RD plus RS. Because you have RS also, you have RD also. So this is by considering it as ID1. So now it is 1.8 minus alpha A into this is 700. Okay, calculate for, okay, with 9973 exponential minus 6. With that it is with 973 microampere, this is coming out to be 1.118 volt. With the ID as 25.6 milliamperes, how much is VDS? Calculate for 25.6 exponential minus 3. Can you see it is coming out to be minus 16.12 volt? So out of these two IDs, which ID is giving a proper VDS? So this ID is giving a proper VDS. So this is the ID now is this. The ID now is this. The current flowing to this is 973 microampere. Correct? The other value, because it is always supposed, we are supposed to find both the values and then decide which one is proper. Okay, let us find what is ID here. So now again, let us find what is VGS. As we saw in the previous case also, VGS is VG minus VS. So this is VG. VG is VDD into R2 by R1 plus R2, which happens to be how much? It is 1.8 1.8 into 170 divided by 390. So this count to be 0.784. So VGS is 0.784 minus ID into RS. So write the ID expression. ID is equal to half Kp W by L into VGS minus VTO whole square. Again, what is VGS? It is this. It is ID into half into Kp W by L 0.784 minus AD into RS minus 0.4 whole square. So again, ID1, ID2. There are two values, two possible solutions of this. So it is alpha equals 100 exponential minus 6 into 60 into 0.784 minus alpha a into 100 minus 0.4 whole square. Shift cal. One of the value is 0.0237, that is 23.7 milliamperes, which is not a possible case. Let me solve for the other value. The value is coming out to be 621.5 microampere. So with this ID as 621, let us find what is VDS. So VDS is VDD minus ID into RD plus RS. So with this into how much is this? This is 5.1 exponential of 3, of course minus of 1.8. This is coming out to be minus 1.369 volt. So this VDS of negative value is not correct even with very less current. So this is naturally ruled out. This is also ruled out, meaning that since VDS is coming out to be even with this lesser current as negative voltage, with this larger current VDS is further negative. So MOSFET is not in saturation region. It's not in saturation region. Then I need to use the linear current equation, then find out what is ID. So how do I find? So I know that linear expression ID is half Kp W by L 2. Okay, this is 2 into VGS minus VTO into VDS minus VDS whole square, VDS square. So now it is, I need to substitute for both VGS as well as VDS. So what is this is ID is equal to half Kp W by L 2 into VGS is 0.784 minus ID into 100 minus 0.4 into VDD minus ID into 5 point or 5100 minus VDD minus of ID into 5100 whole square. This I need to solve. So I am simply substituting VGS by 0. This VGS by 0.784 into 0.784 minus ID into RS. This is actually VG minus VS. So what is VDS now? VDS is VDD minus ID into RD plus RS. That's what is VDD into ID into RS is RD is 5K. This is 100 ohm. That's why it is 5100 ohm. So let me solve this. So here you know everything except ID. You know this, 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 you know this. Except ID, you know everything. These are the only IDs which you don't know. So let me solve for that. So it is alpha A, alpha equals 100 x minus 6 into 60 into, open the parenthesis, 2 into, open the parenthesis, 0.784 minus alpha A, sorry, alpha A into 100 minus 0.4 into 1.8 minus alpha A into 5100 minus of, open, 1.8 minus alpha A into 5100, open, square, close, shift can. So again, you will have two values of ID. This is ID1, ID2. ID1 is, one of them is 334.9 microampere. The other one would be equals minus 1. Let me find the other one. Other one is coming out to be 221.90 microampere. So I have these two. So let me find out of these two what is the corresponding VDS of this. What is the corresponding VDS of this? So VDS of this is VDD minus ID1 into RD plus RS. This is VDD minus ID2 into RD plus RS. I hope you are getting okay what I'm trying to do here. It is 1.8 minus 5100 into ID is 334.9 exponential of minus 6. It comes out to be this comes out to be 92.01 millivolt. The other one, suppose if you replace it by 221, so then it comes out to be 0.6668 volt. So naturally you have this VGS. Of course, what is VDS? Sorry, which is this situation. Okay, now this is a problem corresponding to this. So how much is VGS now? So you have two values of VDS1, VDS2. So corresponding to this value of ID, this value of ID, we can find what is VGS. What is VGS1? It is actually VG minus VS1. VGS2 is VG minus VGS2. So it's actually 0.784 minus of 334.9 into 100. So sorry, 100 micro. This is, let me put that into, sorry, exponential minus 6. So this comes out to be 0.7505 volt. This is one VGS. The other VGS is not too much difference. This is 221.9. This comes out to be 0.7618. So these two are the corresponding VGSs corresponding to these two VDSs. So naturally, when you're corresponding to this, so what is VDS at? VDS at is 3505. So this is VDS sat. So this is VDS sat, this is VDS. So now this is fine. So this is VDS sat, this is VDS. So VDS1 is less than VDS sat 1, so that the current flowing through this MOSFET in this case happens to be 334.9 microampere. Maybe I want all of you to verify this current in simulation, and you can certainly find you won't have a current of this much flowing in the MOSFET with this for this circuit. Again, this answer is electrically not suitable or not possible because these are all mathematical solutions. Fine. Let us see the last one. We're asked to find what is again ID in this. What is ID? If you can see here, whatever VDS is there, this is your drain to source, the same is gate to source. So this is VGS. When VGS is equal to VDS, then what is VDS sat? It is VGS minus VTH. So when you have these two shorted, when gate voltage is equal to drain voltage, so naturally that is when gate and drain are shorted, MOSFET is always in saturation region. Always in saturation region. So let us find what is ID now. So we have the ID expression as ID is equal to half Kp W by L VGS minus VTO whole square, but VGS is equal to of course you can say it as VG minus Vs, which is nothing but VD minus Vs, which is nothing but VDD minus ID into RD. This is your VD, and Vs is ID into Rs. So naturally then VGS happens to be VDD minus ID into RD plus Rs, because when you take out this negative ID as common, so this is this. So now ID is equal to half Kp W by L VDD in place of VGS I'll replace this VDD minus ID into RD plus Rs minus of VTH also. Again I'll get two different values of ID because it's a part of quadratic equation. So it is now alpha equals 100 x minus 6 into 60 into 1.8 minus alpha A into 1000 minus 0.4 whole square shift cal. So again ID1 is 993.11 microampere. The other one is okay. The other one is maybe a larger current. Okay, you have it as 1.97 milliamperes. So naturally 1.79 milliamperes is impossible because that into, so what is VDS? If you consider VDS of this, which is nothing but VDD minus ID into RD plus RS. So what is this? This is now 1.8 minus of 1.97 into, of course 1.97 exponential minus 3 into 1 exponential of 3. Can you see this is coming to be minus 0.17 volt, which is not possible. So the current flowing through this circuit is 993.1 microampere. This is the current ID. So ID is equal to 993.1 microampere. This is the drain current. Okay, these are the different types of MOSFET drain current calculations. So you will find it very handy. So using how to use the calculator to find two different values of ID and to choose which one is proper electrically feasible current. So these are the things which you should do it very confidently. Thank you.